Hey, this is Jack from PhysiologyZone, and in this fourth part on skeletal muscle, we're going to be looking at muscle metabolism and the ways in which muscles source their ATP. So this is going to be a basic introduction to aid your understanding, and hopefully this is going to provide enough clarity that if you're required to study this in depth, this will help as a starting point. So, as we've seen in the previous episodes, ATP supplies the energy for muscle contraction, and without it, no muscle contraction could take place. But ATP also is required in the calcium-active transport pumps on the sarcoplasmic reticulum, which we've seen previously, and you'll find that ATP is used throughout a variety of receptors within our body. But the amount of ATP within muscle fibers for muscle contraction is only sufficient enough to power it for a few seconds. So therefore the muscle fibers require other ways to source their ATP. And to do this, there's three methods which are utilized, and we're going to go through these in turn. They use creatine phosphate, anaerobic cellular respiration, aerobic cellular respiration, and then finally, in the end of this tutorial, we're just going to quickly introduce what the oxygen debt is and how we repay it. So creatine phosphate is a molecule which can store energy within its phosphate bonds. So whilst a muscle is relaxed, they produce more ATP than is required for their resting metabolism. And this excess of ATP transfers a phosphate group to creatine, producing ADP, adenosine diphosphate, and creatine phosphate. This acts as a very quick energy reserve for creating ATP. So when a muscle starts to contract and requires that energy, creatine phosphate transfers its phosphate group back to ADP in a reaction which is catalyzed by the enzyme creatine kinase to form creatine and adenosine triphosphate, or ATP. So the ATP can then be used to create muscle contraction. So this type of energy source is extremely quick, but it unfortunately only lasts for approximately 15 seconds due to finite amounts of creatine. So this system would power something like a 100-meter sprint. And on a side note, creatine supplementation is widely used as a performance-enhancing supplement. So it makes sense that if you increase the amount of creatine within the sarcoplasm, you're therefore going to increase the amount of readily available creatine phosphate that can then allow the production of more ATP. So this, of course, is best for exercises which require large amounts of strength and power output. There is obviously a limit to this, and people differ in terms of their response to creatine supplementation, and there are also some concerns regarding its safety due to large intakes and prolonged usage of this supplement. So as the ATP produced by creatine phosphate is depleted, the muscle turns to glycolysis as a method by which it can source its ATP. So glycolysis is an anaerobic process by which glucose is broken down to produce ATP in a series of 10 steps which are beyond the scope of this tutorial. However, glycolysis cannot generate ATP as quickly as creatine phosphate, so ATP is provided to the muscle slower. The glucose used in glycolysis can be gained by either glucose which diffuses straight into the muscle from the blood, or glycogen which is within the muscle tissue. Now glycogen is a polysaccharide, so it just has tons of glucose molecules stuck together, like as in up to 20 or 30,000 of them. And glycogen must first undergo glycogenolysis to make glucose available for glycolysis. So the input point is one glucose molecule, and that glucose molecule undergoes the anaerobic process, which is called glycolysis, and that is a series of reactions that ultimately produces 2 ATP molecules and 2 pyruvates. As a quick side note, your text might talk about pyruvate or pyruvic acid, and so long as you're not studying biochemistry, they are functionally the same thing, so in terms of physiology, they will be used utterly interchangeably. So pyruvate can then be used for one of two things. If we have no oxygen available, it's then broken down from pyruvate into lactic acid, and this is an important process which we're just going to touch on a little bit more now. So pyruvate with the reduced form of something called nicotinamide adenine dinucleotide, which is the NAD, and the H on the end just means that it's the reduced form of that molecule, with a hydrogen, is catalyzed by the enzyme lactate dehydrogenase. And the job of this enzyme is to take the hydride group from one molecule and put it onto another. So this reaction by which pyruvate is converted to lactate is called a redox reaction. Now these are very important physiologically and occur throughout the body, and redox just refers to one half of the reaction being reduction and the other half being oxidation. So pyruvate gains electrons and becomes lactate, and that part is reduction, and the other half is oxidation. So our reduced form of nicotinamide adenine dinucleotide, the NADH, is oxidized and loses electrons to form nicotinamide adenine dinucleotide in its oxidized form. The importance of that molecule is that it allows glycolysis to keep going, and it's the only thing that can allow glycolysis to keep going. Ultimately, glycolysis comes to an end because it can't be sustained for very long because of its inefficiency. It makes 2 ATP molecules per 1 glucose molecule. So after about 1 minute, the anaerobic respiration process is completely depleted, so it's not much good for anything more than, say, a 400-meter race. What we have to use is aerobic respiration. So this is where, if during the glycolysis process in the production of pyruvate we have oxygen available, this pyruvate then enters aerobic respiration, which is what we're going to talk about now. Aerobic respiration is the breakdown of glucose or other nutrients in the presence of oxygen to produce carbon dioxide, water, and ATP. There are 3 important inputs for aerobic respiration, which are the pyruvate or pyruvic acid, fatty acids, and amino acids. So firstly, the glucose, which is broken down by glycolysis, produces our pyruvate, and that's what's being used first in our aerobic respiration. But when we are low on glucose and its immediate polysaccharide glycogen, then the body turns to fats to make fatty acids and glycerol, and these can then enter aerobic respiration. And finally, when protein is high or if glucose and fat stores are very low, then via a series of reactions they can be broken down into amino acids, which can then be used in aerobic respiration. So this process all occurs within the mitochondria, so the powerhouse of our muscular fibre, and it's in the presence of oxygen from either hemoglobin, so oxygen that we find in the blood, or from oxygen which is attached to myoglobin, the protein within the muscle fibres that binds up oxygen. Our pyruvate fatty acids or amino acids can enter aerobic respiration, which occurs in a 2-step process within this mitochondria. First, they enter the Krebs cycle. This is also known as the TCA or citric acid cycle. So that's 3 names for the same thing. They then, following this, enter the electron transport system. Again, the details of this are beyond the scope of this tutorial. The outcome is ultimately to yield carbon dioxide, water, and our ATP. And this is much more efficient than our glycolysis because you get 36 ATP molecules per glucose molecule and 100 per fatty acid. Now, this is obviously much more efficient in terms of yield, but unfortunately it requires a steady stream of oxygen, so it's much slower. But if you're doing moderate activity, like walking or a very steady jog, then this system is primarily used to provide our ATP for muscle contraction. And interestingly, after exercise, you'll probably notice that despite having stopped, you continue to breathe quickly and deeply. And the reason for this is due to what is called the oxygen debt. This is the oxygen that's required to compensate for the ATP which we have had to produce without oxygen during our exercise. So you are literally paying back the oxygen. And the way that this is done is in 3 ways. Firstly, it's used to convert lactic acid into glucose or glycogen stores, which can then be put into the liver, to resynthesize creatine phosphate from creatine, and to replace the oxygen that's been removed from our myoglobin in our muscles to make our oxymyoglobin. You can breathe like this after exercise for a few minutes, or if it's really strenuous exercise, then this can last several hours. And as a final extra note, it's interesting to think what causes your muscles to fatigue. So you'll notice that at some point during continuous use of our muscles, the speed and the force of their contraction slows down. And this is because they are no longer contracting effectively in response to signals from the nervous system. It would appear logical to think that this is because we've run out of ATP, but in fact, multiple studies have shown that the ATP within our muscles at rest and fatigue are relatively unchanged, and we have correlated other things that we think are involved in fatigue, including lactic acid buildup, which makes the intracellular pH more acidic and stops the enzymes working correctly, inadequate release or reuptake or some sort of leaking of calcium out of the sarcoplasm, which is affecting contractility, or failure of action potentials to release enough acetylcholine at the neuromuscular junction, and that's just naming a few. But ultimately, the truth is, we don't really know yet. But the purpose of the fatigue is obviously to prevent significant injury to our muscles. So that's everything I wanted to go through. So just to recap what we've been through, we looked at creatine phosphate and we saw how ATP is in abundance in the resting muscle and is combined with creatine to form creatine phosphate, which can then be used to give up its phosphate group to ADP and make that ATP as its initial energy source. But remember, this is very quick and it only lasts for about 10 seconds. We have anaerobic cellular respiration, which is where we use glucose from the blood or in the muscle, and that undergoes glycolysis, which is that anaerobic 10-step process that produces ATP, 2 molecules of that, and 2 molecules of pyruvate. Now, the pyruvate can be broken down to lactate or lactic acid if we don't have any oxygen, but if we do have oxygen, then it may well go on into aerobic respiration. So aerobic cellular respiration uses our pyruvate and fatty acids and amino acids, and they undergo the Krebs cycle or the TCA or citric acid cycle within the mitochondria to produce 36 plus molecules of ATP. After exercise, we have to repay our oxygen debt, and that oxygen is used to reproduce glucose or glycogen, which can be stored, creatine phosphate, and oxymyoglobin. So I hope you found this tutorial useful, and we'll see you in the next one, which is the final episode on skeletal muscle.